everybody. Thank you for joining us today. This talk is by Corey Overstreet, a senior security consultant at Red Siege, and he's going to be talking about payload development today. So go ahead, take it away.
Awesome. Thank you. Hey, thank you. All right. So, yeah, the name of my talk is That Shouldn't Have Worked, Payload Development 101. So this is who I am. That's me with some shorter hair. I've done a few things, got a few letters after my name. Anyway, so the who and the why for this talk. I kind of have to talk fast, by the way, because there's a lot of stuff here. I'll have a link at the end where you can download the slides for reference later. But so this talk, so I wrote this, as with all the talks that I do, I wrote this for, you know, I wish I had had access to something like this when I was kind of moving into red teaming. Excuse me. There we go. But one thing we do get asked by a lot of our clients afterwards, is, you know, a lot of the defenders is they say, okay, that's awesome. You guys come in year after year, you know, you kick the doors in, you do your thing. What can we be doing to prepare for the other 51 weeks that you guys aren't here out of the year? So I kind of wanted to throw this information out there so that if you are a defender, you can also kind of follow along with some of these things and just try it in your environment as well. And, you know, there's a quote from a guy that shows up for our Wednesday offensive that we do. He said, you know, everything's stealthy until you're watching for it. And what he's getting at is, you know, there's a lot of things that are just dead easy to catch, but sometimes you're not necessarily watching, so it'll just slide right by. So, you know, when you're talking about payload development, it really is a cat and mouse game. I've had things where I finally, after 3 days, I finally figured out how to get my payload up and running, got around the EDR, thinking everything's great. Going into the weekend, I come back on Monday with my head held high, just to realize all my beacons are dead, and they caught it. So, you know, just remember that whatever works today might not necessarily work tomorrow. Keep it simple. I've literally went down the rabbit hole of writing crazy shellcode loaders just to realize a PowerShell script would have done just fine. You know, so just try to keep it simple. Try to make sure that you're not necessarily pigeonholing your ideas. But if you are a consultant that's jumping into different environments every week, every environment really will be different. I've had 3 different, you know, I'm not picking on any particular EDR vendor here, but I've had 3 different like Carbon Black or CrowdStrike customers, and what worked in one of them didn't work in either of the others. It got caught right off the bat. So just make sure that you're trying as many different things as you can, not just necessarily that one thing that worked that one time. And then, to be clear, nothing in this talk is going to be new or groundbreaking or anything just mind-blowing, but it might be new to you and your team. So there are a lot of interesting things that I kind of wish I had known along the way. So to give credit where credit's due, you know, I want to call out the researchers, the open source tool writers. Those guys are really the people who need to be praised here. That's me at the bottom, just running around acting like I know what I'm doing. So, real quick, we're going to kind of walk through a few initial considerations, things that we think about when we're, you know, just right at the beginning of the test. Then the initial protections and detections that we have to get around, usually on a Windows box. Most of this is going to be focused on Windows because that's 90% of what we see. And then after that, we'll talk about getting out of the detection sandbox, and I'll explain that a little more here in a minute. Then we talk about static detections. This is when the file has to live on disk for a little bit, you know, during your persistence or during your lateral movement. And I'll run through a few of our common execution methods, and then there'll be a slide with some resources at the end. So for initial considerations, first thing we have to think about, what programming language do we want to use? The first and foremost, we use C and C++. You know, that's pretty much the go-to for malware, but it can also be a pretty big indicator. So sometimes we try to blend in by using stuff like .NET. This would be like PowerShell, C#, and even F#. We've started using F# a little more, but it really is kind of a pain to work with. And then not as much nowadays, but with VBA, getting a macro executed in HTA, excuse me, or some kind of VB script, something like that. Less common, sometimes we have to go the route of using Rust or Golang. It's not that we avoid them, it's just that we're not as experienced in writing code and that kind of stuff. And when you've only got a week to kind of get this done, you don't have a lot of time to kind of learn on the fly. So we do use it some, but it's mostly modifying examples that we can find. Every now and then we'll have to go down the path of NIM, and then Python, as long as the Windows store is available on the endpoint. Sometimes we will actually just use Python. So, of course, common file formats, you know, top of the heap is portable executable. These are your exe files. This, you know, is going to be one of the most common things that we use, but you can dress them up in a lot of ways to get around detections. Of course, you've got DLLs as well, but then we use a lot of .NET code embedded in XML files, and we'll get to that later on during the common execution methods. But some of the other ones we like to use, especially during phishing, would be something like an MSI file. You know, during your social engineering, you might convince them that they need to install something, but MSI files are actually really great file droppers. And then if you're trying to do persistence, if you have access to write to the registry, there are special DLL files that export certain functions that will work automatically with Word and Excel. Those are the WLLL and the XLL files. And then, you know, a lot of these other ones look pretty common as well. The click once applications, pretty much if you can write code in .NET, you can actually just publish it as a click once application, host it on a website, and they can actually download that straight from a link. So a lot of times that's a different way of getting your .NET code up and running. So something that we have to stress to, especially the defenders who are trying to do this, they say, well, you know, it's crazy. Like when you guys were here, you downloaded it from the web and you still got it to work. Whereas when we hosted it on a web server outside the outside of our environment, we couldn't get it to work. The Windows Defender Smart Screen kept popping up, and that's because of you know, they didn't actually go through all the same steps that we did. So when you are testing this against an environment, you need to make sure that you're not just copying it over through RDP or something like that. You need to actually simulate what the real attacker would have done, which is download it from a remote location using different tools like, you know, obviously a web browser, but you can also use like a PowerShell download cradle. You can use the bits admin utility or even curl. Curl's built into Windows as of one of the versions of Windows 10. But one of the things that gets attached to it is an NTFS alternate data stream. So what this is, you might have heard it referred to as mark of the web. Basically, it indicates to Windows that this file came from the internet. And there are ways around that, but if you do not get around that, that's why you see the Defender Smart Screen popping up whenever you try to run that executable. So that last line there is actually a PowerShell command where you can view the zone identifier or the mark of the web. So some of the ways we get around that, first and foremost is a dropper. So this is where you just encode the file, you know, embed it within something, and then use some kind of execution method to pull that back out, whether it's base64 encoding it, AES encrypting it, or encoding it some other way. Another way around is to use containers. So like 7-zip is still pretty notorious for not attaching mark of the web, at least by default. Windows also has the tar archive utility now, and that still does not attach mark of the web. It's been reported to Microsoft quite a few times, but they just haven't got around to fixing that yet. Another one is to use like a container like a virtual hard disk, like a VHD or a WIM file. But if you're going to use this in a phishing campaign, this does have to be mounted as an admin. So used to be you could mount an ISO file or a virtual hard disk as a regular user, but that's since been removed. And then Microsoft took it a step further with the ISO files, and they actually started attaching mark of the web to all of the files within the container. The vulnerability, I kind of skipped over that. The vulnerability used to be that the container file itself would get the mark of the web, but all of the files within would not. So when you extracted them, now Windows has no idea where those files came from, therefore it just allows them to run. So this is the mark of the web that I was talking about. Basically, I made this executable, threw it up on a web server, downloaded it, and as you can see there, why is my laser not working? Yeah, whatever. So at the top there in the red box, you can see that it came from the internet, and it marked it as something that needs to be scanned as it's being ran. But then I did the exact same executable file, put it up in a tar archive, put it on the same website, downloaded it, extracted it, and as you can see, there's no zone identifier attached to that file. So again, Windows has no idea where this file came from. So we've talked about a few of the initial things that we think about. So let's talk about some of the, just right off the gate, these are the things that Windows is going to look at, and this is how it's going to scan for malicious or suspicious things. So first and foremost is the AMSI, the anti-malware scanning interface. This is loaded into every single process that runs on Windows through AMSI.DLL. This is how Microsoft Defender performs the antivirus functions that it does, at least for the most part. It's loaded in userland, and because it's loaded in userland and not some high privileged process, it can be bypassed, but the bypasses are also being signatured, so you kind of get back into that cat and mouse game. So let's talk about some of the bypasses. First and foremost, you can just go through and figure out what is actually catching your payload from Defender. So there are tools like Threat Check and Defender Check where it will go through and it'll slice the malware up until it figures out the offending string that Defender just doesn't like. So you can go in, change your code, you know, and Bob's your uncle, all of a sudden your payload's just sailing right past. Another thing you can do, you can actually write code to zero out the AMSI scan buffer. So you patch the AMSI DLL in memory and you just say that the scan buffer is set to 0 bytes. So because nothing fits in there, it just says, all right, well, it passed its check and it moves on. Another thing you can do is there's a function called AMSI init failed. Basically, it just tells the AMSI DLL that AMSI did not initialize correctly. So from that point on, you actually don't get scanned by AMSI anymore. Another one is just to use older tools that have no AMSI integration, like PowerShell version 2. This, as long as .NET version 2 or 3.5 is installed, this should be able to be launched. In Windows 10, it used to be default. Now I think you actually have to enable it. But because there's no AMSI integration, there's no visibility into the process. That website at the bottom, AMSI.fail, will give you randomized AMSI bypasses in PowerShell. Basically, every time you load the site, you get a new version of a bypass that works against AMSI. So Microsoft realized how fragile the Defender detections were, so they came up with the Event Tracing for Windows, or ETW. So basically, instead of just looking for, you know, malicious strings or malicious bytes within a signature for antivirus, now they've started looking at the events that your malware causes. So this would be like, you know, it's automatically calling out to the internet as soon as it's ran, it's calling out to suspicious domains, it's moving memory around in a suspicious way. It can actually trace those events now and then look for patterns in that are known to be malicious. A lot of EDR products actually have custom consumers for ETW, and they come up with their own signatured series of events to look for as well. All of these API calls are usually contained within ntdll.dll, which also gets loaded into every process. And this can be bypassed in mainly the same way as AMSI, but again, the tampering can be detected, so you get back into the how do I do that without getting caught kind of thing. So obviously, just like with AMSI, obfuscate your tooling. Sometimes it's as dumb as just changing some of the function names from Mimikatz to Mimidogs. Change the namespaces in your .NET code. Change the default title, product, GUID. A lot of that third bullet point there, when you download tools from GitHub, those all have a default title, product, GUID, the product ID. And if you sometimes all it takes is just going in and changing those. You can literally just increment the numbers by 1, and that's enough to get around it sometimes. Again, you can patch those API call hooks. So this is where ETW would be sending all of the events as you're going to the consumer, but you can patch that out so that it just doesn't do that anymore. And in a lot of cases, this can be enough to at least blind EDR at first, but there's still a lot of other things going on that can still be monitored. So we kind of talked about hooks a little bit. So as far as the hooks go, what we're talking about here is the EDR products will actually go through the DLLs that get loaded, and they're watching certain Windows API calls. And the way they watch those is, instead of actually loading the API call the way Microsoft intended, they'll patch the first instructions of that API call to immediately jump into the space of the EDR DLL. So if you look here, the one in red, it immediately starts with a jump instruction. That's a dead giveaway for the most part, that is probably something that's been patched by some other security product. A legitimate one would show, you'll see that it starts with a move instruction because it's going to push something onto the stack and then pass that on to whatever API call you were trying to call. So the way we can unhook these is we can actually just walk each of the API calls in memory and just overwrite it back with the stock bytes. But that gets a little cumbersome because those DLLs do change between versions of Windows. They might even change just from a simple Windows update. So what you can actually do instead is just literally pull the DLL off of disk and copy it back into memory. So it puts a clean copy back into memory, and none of the hooks will be there afterwards. There's a tool written by a guy at Black Hills, Matt Eidelberg, called Freeze. What it'll do is when you start your process, it will start another process like Notepad or something similar, but it'll start it in a suspended state so that it can pull the DLL out of memory of that process and patch it into your space so that you're clean again before you start execution. But all of these things can be detected. So again, it's all in just what works in your environment. So another way that malware writers started getting around these checks and around these hooks is to use Syscalls. So in Windows, there are certain privileged API calls that users still need to talk to. These would be things like graphics drivers or certain like token privilege checks. If they gave users just carte blanche access to those, then that would be a privilege escalation nightmare. So what they do is they make these filter API calls where basically all it does is it checks to see, do you have the privileges to execute this? If so, then we set the stack up and then we perform a syscall, which will bump it over to a higher privilege process. But because you have that proxy in the middle, now the user doesn't necessarily gain access to that elevated privilege. Now, where syscalls come in handy is a lot of those NT or ZW API calls, we can just basically do the same thing ourselves. We can just write assembly that does the exact same thing, and we can just cut out the middleman and go straight to the privileged API call. A lot of times this can be stealthier than userland API calls, but there's ways to detect this too, especially if we're just not calling these proxy function calls. No program does that legitimately. So if you wanted to generate these syscalls, there's tools out there, SysWhispers 2 and 3. Really the only difference with 3 is that it supports 32-bit Windows API calls for the most part. And then the guys at Sector 7, they came out with a couple ways of kind of indirectly figuring out where these syscalls live and what they look like in memory dynamically at runtime. That's the Hell's Gate and the Halo's Gate methods. It would take me a while to explain those, but for the most part, it basically just walks memory looking for the API calls that you want and then indirectly calls them. And unhooks the call before calling it. And then you can also just do unmanaged assembly code straight in C#. It's a bit of a learning curve, but it is possible. So these are some different ways to generate the syscalls to get around those EDR hooks. But again, these are all things that are heavily monitored and can be caught depending on what they're looking for. So we've talked about some of just right out of the gate. Here's how we got caught. So let's talk about the sandbox. So let's say we bypassed all of that stuff. You know, antivirus and EDR are at least happy for that microsecond that we double clicked it. Now it's going to detonate your payload in a sandbox. A sandbox is like a small virtual machine that either runs locally or remotely in the cloud by your endpoint protection vendor. Microsoft Defender does this too. If you look in the Defender configuration, it'll say the cloud-based protections. That's basically what it's doing. And the reason for this is so that if you were to bypass the sandbox locally, even if they send it off to the cloud, they can notify all of their customers immediately if this is something that's malicious. So the way you can tell you're in a sandbox, though, can be determined programmatically prior to detonating your payload. And we'll kind of talk through a few of those in a minute. But the reason we would want to do that is to make sure that we're not going to be just completely murdered right out of the gate. So one of the first things we like to use is time. So the name of the game is you slow down execution. EDR and defensive products cannot hamper the user from performing the actions that they need to perform on their computer. So if you slow down execution long enough, the EDR more or less has to just let it go because it can't stop the user. Otherwise, you've got unhappy customers who will uninstall your product. So one of the easiest ways to do that is just using Windows API calls. There are sleep calls or suspend calls just to let it sit there for a minute. The only problem is, you know, EDR also knows about this, so they, the vendors do. So what they'll do in the sandbox is they'll actually just speed up time. They'll move the clock forward however many seconds are detected, and then continue execution as if nothing happened, and then your payload executes like it was supposed to. And just the simple use of those sleep API calls can be detected. So one of the ways we get around it is to calculate large prime numbers or calculate the Fibonacci sequence. The only problem with these is it grows exponentially. So you might get a 30-second pause, or if you go too big, you might get a 30-minute pause. So you want to make sure that you don't go too crazy with it, or your payload will just never execute. But kind of like I hinted at there at the beginning, you know, the security products are there for the security of the user, but they can't stop the user from using the computer either. Otherwise, you know, what's the point? So another way to get around the sandbox is through size. So the name of the game is just make it too big to fit in the sandbox. We have literally had where we ran straight up Metasploit payloads in 2024. And we just inflated them to 700 megabytes, and EDR just let it go. But some of the tools that we use, a guy on our team, Mike Saunders, wrote a tool called DigDug. Basically, it can either generate junk data or data from the dictionary, where it just takes dictionary words, and it will append that in the text section of the executable, and it'll make it 700 megs. Now, the problem with that is it doesn't compress very well, so now you got to send a 700 meg file into an environment. So a way around that is, I mentioned him earlier, Matt Eidelberg wrote a tool called Mangle. This just uses zeros instead. Because it uses all zeros, when you've got 700 megs of zeros, when you go to compress it, it'll go back down to its original size. Now, when they take it back out of the the container file, magically it's right back up to 700 megs, and the sandbox doesn't see a thing. So again, kind of like we talked about with hindering the user experience, they don't want to sit there and scan 700 megs of data, so it'll just go, it's too big, whatever, and just move right on. Another thing you can look for is the computer that is scanning this file connected to a domain. So, again, we talked about this was in a Windows environment. So just check and see if it's domain joined. That's actually, domain joined is an API call you can check. And as long as it comes back good, you just let your code continue. But a lot of times these sandboxes are just a small, tiny virtual machine that is not connected to the domain. It's just spun up for the sole purpose of checking that malware for certain things, and then it's tore back down. So the only problem with checking for domain status, though, is if you wanted to use the domain name, like as a guardrail for execution, you kind of have to know that ahead of time. So you kind of get into a chicken and egg problem where you have to know that before you write your malware, but you don't have access into the environment because you haven't written your malware yet. So these can be gotten through social engineering or some other means, but for the most part, we start using that kind of after we've landed inside the network. But that will get around the sandbox just because, again, those little virtual machines are not connected to the domain. So there's a whole other list of things that we can look at. The monitor resolution, a lot of times there's not even a monitor attached because these things are running in memory. The amount of RAM is extremely minimal. Nobody's running with 256 megs of RAM these days. The MAC address. The MAC address is probably a known virtualization host, like VMware or something like that. You can look at the number of processor cores. I guarantee you it's probably going to be 1 on that sandbox, so that nobody runs with a single core nowadays. Most every PC that comes out has at least 6, 8 cores. You can look at the executing username if you want to get that granular, but again, you kind of have to know that ahead of time. Plus, now you have to write your malware for every single user that you land on. So you can also look for debugging processes. Again, there's a whole list of these things. So there's a GitHub repo out there called Check Please. Brandon Arvanaghi and Chris Trunzer wrote a repo of all these different code samples for ways to check each of these things. And they even broke it down into host-based and user-based attributes that you can look at. So the cool thing too is that code, basically you can take and embed them. So you can have like 6 of these checks all in a row, and as long as your code passes all 6 of those, then you let your code detonate. Otherwise, it just does something inert and moves on. So we've talked about, how do we get up and running, but what if we need to leave that malware on disk? So that's what we're talking about when we talk about static detections. So occasionally the security products are going to come along. They're going to scan looking for malicious strings in memory and on disk. So most of the time we're trying to get, some kind of position independent binary shellcode up and running. These have to be stored within the program. If you're calling out across a web proxy, that's usually enough to get you caught, especially if it gets scanned on the way in. So if we can send it in such a way that it doesn't get detected automatically, then it can live on disk as long as it's not being detected that way too. And one of the ways that they detect it is if it's highly random data all over a binary, and that highly random data keeps getting accessed, that can be an indicator that something funky is going on. So how can we get around that? So one of the ways is to store it using known or common data types. One of those would be like a UUID or a GUID. These are like a 32-character alphanumeric string of characters, but they follow the exact same as hexadecimal code. So you just store it in 32 character chunks, and you can store a whole array of those, and now you've got all your shellcode in memory. Another one is just to throw it on the end of something that's highly random anyway, like an image file. JPEGs, PNGs, GIFs, you know, if you just append this on the end, or at least throw it in the middle, and then programmatically retrieve that at execution, you can get up and running, and most of the time it's not going to get caught. One of the guys on our team, I mentioned him earlier, Mike Saunders, he had a pretty novel idea of just mapping those bytes to lower entropy data. So much like with DigDug, he took dictionary words, and then at each time he encodes stuff, he picks 255 random words from the dictionary file and maps each one to a possible hexadecimal byte value. So, you know, 0x01, 0x02, all the way up to 0xFF. And then you just store that array of English words in memory. Most programs are going to be doing that anyway, so it actually looks completely legitimate and it'll fly under the radar. And then as long as you use different words or different encryption keys each time, you know, it's easy to get around those signatures using stuff like that. So another thing are the signatures. This is where, again, the antivirus comes in and it's looking for those telltale signs that something out of the way is sitting there. So a trick I picked up from the White Knight Labs guys is different compilers optimize your code in different but predictable ways. So if you use Visual Studio to compile your code, or the C# compiler that's built into Windows, those kinds of things, that can actually be signatured. So if you just literally use any other compiler out there, a lot of times that's enough to get around the signatures, because the bytes are not going to be linked together or compiled in the same way. Another thing to think about is if it came from GitHub, it's signatured. The day it goes on there, all the security vendor products are scanning for these, you know, malware loaders. They're scanning for the next threat that's coming along, and they're writing signatures as fast as they can. A lot of it's automated. So if you're going to use stuff from GitHub, just make sure you're going through and trying to figure out where those signatures live and what you can do to change them. Another thing is if it's an off-the-shelf C2 framework like Cobalt Strike, Sliver, Covenant, they're all the default payloads are signatured. There are ways to go through and modify that. There's a lot of scripts out there that can go through and at least change the default indicators. So we put a lot of time and effort into changing those so we can get up and running as well. But we're using pretty publicly known techniques for modifying those. A lot of times it's literally just changing the size of a variable that always gets used. So some of the stuff, we kind of talked about this a little bit earlier, but you know, just change the variable names or links, change the checksum of the final hash or the final payload. You can literally just append some junk data to the end of an executable. It'll still run, but it completely changes the overall checksum of that file. And like I said in the last slide, you can change the default encryption keys. A lot of times when we're writing our generators, we use a random word, we encrypt with that or encode with that, and then just flip-flop when it runs. Another thing with modifying the C2 framework detections, there for a while, Cobalt Strike had a script where you could just run it each time you started Cobalt Strike, and it would actually modify all of the code and recompile the base images that it used, and it would change a lot of the default indicators on its own. Now again, there's still other ways that other things that they can't change, and that's what the EDR vendors are watching now. But those are things that you can look into when you're trying to see if your environment will catch these. Another big thing is the order of operations. So malware is going to follow the same order of operations. It's going to provision a memory space. It's going to copy your payload into that memory. It's going to make that memory space executable, and then it's going to run it. So what we like to do is we just throw needless spaghetti code in there just to break up the order of operations. So we provision the memory space, and then we just increment a number 3 billion times. We copy our payload into memory. We go check the value of this pointer 6 times. Then we make it executable, and then we go back and increment that number back up to 3 billion again. And then we execute our payload. All the while, we'll throw little sleep statements in there or something too, just to kind of make it so that it's completely randomized and it gets around that order of operations. So some of the things to think about as far as being suspicious right out of the gate is if your C2 calls back half a second after you execute, a lot of times that can be enough. If it's not calling back to a reputable domain, that can be enough to stand out as suspicious or just outright malicious. Now, a lot of programs talk to the internet, but if they're not talking to something that's pretty well known, that can make you stand out. So again, sleep or do some junk code there at the beginning. Something else is the parent-child process tree. So everything you run in Windows, when you double-click a program, it is now running as a child of explorer.exe or as a child of command.exe or PowerShell. Because those are the things that are executing it in memory. But now you have a relationship between those things that can be traced. So, you know, I kind of threw this in there kind of jokingly, but it is something that does get watched for is, you know, why is Microsoft Word executing command.exe? That's not something normal. Why is Microsoft Edge now calling PowerShell? You want to make sure that all of this makes sense and that you're not executing something that immediately stands out because it's out of the norm. Another thing is if you inject into processes, think about what is talking to the internet. We always target things like web browsers or chat clients because those are supposed to be talking to the internet. Notepad should never be talking to the internet, like ever. So if you inject into Notepad, which is the default for a lot of the programs you download from GitHub, that's probably a pretty big red flag. And then another thing is when you're writing malware, you know, the hip cool thing used to be to just make the memory readable, writable, and executable all at the same time, but no program does that anymore. They make it writable, they write stuff into it, then they make it executable, then they execute. So if you are making your memory space that you're copying your payload into all 3 of those things at the same time, a lot of times they get shut down just right out of the gate. So we'll kind of go into some common execution methods here. So like I said at the beginning, executables, you know, these are still the #1 thing we use. So there's 1,000,001 ways to execute a portable executable. Again, when you double click it, when you run it from a shortcut, when you run it from literally any program, it's going to run under command.exe or PowerShell.exe. But there are ways to get around that. But if you name it right, if it's in the right folder, if it's a child of the right process, it blends in. And a lot of times that's really the only sniff test that you have to pass. You know, once you've gotten past all the other things. But they are highly scrutinized. Like even my grandma knows you don't run an executable that you downloaded from the internet. So, you know, it can be detected just right out of the gate because your social engineering target or the blue teamer who's looking at their logs is going to start being suspicious if they see an unknown executable being executed in their environment and they're getting alerts about it. And then if they have application allow listing, this can just be outright blocked. So with application allow listing, you kind of set a baseline for, as a defender, for the executables that can run in your environment. And so if this came from the internet or if it's an unknown thing, it's very possible that this isn't going to be allowed to run. But, you know, when you do it right, it seems to just work 100% of the time. So, like I said, here's different ways that we execute these things. So obviously, command.exe, PowerShell.exe, those are your command shells. That's usually how you're going to execute. But one thing we like that I found is the explorer.exe binary has a flag called the separate flag. So you've already got explorer.exe running on your system. If you run your payload executable as an argument to explorer.exe with the separate flag, it'll start up a new explorer process with your binary as a child of that process, and then the secondary explorer.exe will actually die, and now your process is running in memory with no parent, which works in your favor, because when the ETW scans start coming along, they actually unless they're scanning for other things, won't see a suspicious parent-child process tree there, and a lot of times will allow it to keep running. MSI files, under the right circumstances, these can lead to privilege escalation depending on how the users are configured. But these are awesome droppers as well, so you can drop things to disk and execute them. MSIs can run scripts before and after the supposed installer. So a lot of times we'll impersonate a legitimate installer like Zoom or WebEx, something like that. But we also ran our DLL ahead of time as well. Shortcut files. So if you do the right social engineering, you can make a shortcut file look like a PDF that runs that hidden DLL that was sitting in the same folder. We use that a lot on social engineering type things, at least if we can get a container into the environment without much issue. And then service binaries. So this is in Windows, when you have things that run at startup, they are running as a service. 95% of the time, they're running as system, which is the highest privilege level out there. So if you have write access to where a service lives, or if you're an admin on the box, you can actually install a service yourself or replace a service binary. And now you've pretty much got persistence till the end of time, or until you get detected. So another very popular thing that we use is MSBuild. So the MSBuild is the .NET compiler. This is built into every copy of Windows from Windows 10 on up. But it can execute .NET code as long as it's in an inline task file. These are XML formatted files, but you can literally just throw .NET code in there and it'll compile and run it. The command is literally as easy as wherever MSBuild is living, and then your XML file. You can even call out to the internet and have it download it from there and run it from like a WebDAV share. So this will bypass application allow listing because it's signed by Microsoft. By default, most, if not all, allow listing policies are set up to allow all Microsoft signed binaries. And these XML files, as long as you encode them right, coming into the environment, they can bypass the static detections because it's just text, as long as they're not seeing any malicious strings inside the file. So another cool trick you can do with MSBuild is you can actually change the XML file. Don't change anything in the file. You literally just change the file extension to CSPROJ or C# project file. As long as it's in the same directory as MSBuild, you can double click MSBuild, you get execution. So one thing we like to do is copy MSBuild and the payload file to the same directory, and then throw a shortcut in the startup folder, or set a service, set a scheduled task, something like that, to execute that MSBuild. But the cool thing about that is in the event logs, it's only going to show the execution of MSBuild. It won't actually show the argument with the payload file, as long as they're in the same directory. And kind of like I mentioned on the last slide, you can load the C# code from a WebDAV share. So you download the inline task file, keep the C# code outside the network, and then have MSBuild reach out and pull that C# code down and load it. Now, That creates a lot of indicators because, you know, now MSBuild's calling out to the internet, and it's also downloading across your web proxy. So, you know, it's kind of, you know, you take the risk if it's worth it. But the cool thing about .NET is you get access to all Windows API calls, basically, and you can do the Syscalls, you know, if you figure that one out. And so now you've pretty much got a pretty capable code execution technique from something built into Windows. This is another one that's also built into Windows, is the InstallUtil. So this is the .NET install and uninstall utility. Again, it's sitting in the same folder as MSBuild. It's on every copy of Windows out there. And it's also an application allow list bypass because it is signed by Microsoft. Now, the only problem with this one is you have to have a compiled DLL or executable sitting on disk for this to work. So you're going to have to get around the static detections. You're going to have to get around a lot of the other disk scanning utilities that are going to be looking for things. Also, because of the nature of this, if you inject into the InstallUtil process, that can be an indicator of compromise because now you've got InstallUtil running for days or weeks on this host if you stay in that process forever. So it's just as easy as running InstallUtil/u for uninstall with the payload. One thing we like to do with social engineering, we'll you know, take apart an MSI file for like Zoom install. We'll throw our DLL in there, and then we'll modify the shortcut that would execute the Zoom installer to execute our DLL, and then launch the installer for the Zoom client. And that way we get up and running with our code, but then they also see what's expected, which is the Zoom install. And that has worked very well. But again, link files are being scrutinized more and more during execution. So this is probably one of my favorite methods, at least on Windows 10. Windows 11, they've started fixing the path environment variable so that it makes this a little more difficult, but it's not impossible. So a proxy DLL exports all of the legitimate DLL function names that is expected of something that a program is looking for. But then it will forward any of the function requests onto the real DLL while also executing your code. This is a legitimate Microsoft function in Windows. It's designed so that you could just kind of drop in place, like an update to an application or a function, and you kind of shim your code in to it. But we can also use the exact same functionality. And by default, pretty much every Windows program out there is susceptible to some form of DLL hijacking. So a lot of them are looking for default DLLs, like those that are found in System32 and SysWow64. And they look in their own folder first, and then they start walking through that path variable, looking in all of those folders for that DLL. So if you have write access to where this application lives, or if you can just copy the application somewhere where you control, you can drop this proxy DLL. And the good thing is because it's actually being able to talk to the real DLL through that proxy, your program won't crash. It'll run like it's supposed to, but now you've shimmed in your malware. So I threw the name of a tool down here, the Spartan Proxy DLL Generator. That's a tool out on GitHub that can do proxy DLLs and COM hijacking. But if you want to play around with that. So like I said, one of the things that I target, especially if I see that I've got write access to a folder where a Windows service binary lives, but I don't have the rights to stop or restart that service, a lot of times what I'll do is I'll pull the service binary, see if there's some kind of DLL that it's looking for, and then I'll create a proxy DLL targeting something like version.dll that I mentioned on the last slide. That is called by just about every Windows program out there, and it's pretty minimal in its functions. So let's say there's a program in the user's app data folder, or you do have write access to that service binary folder. You just drop your proxy DLL in, and then the next time that system is restarted, you will get code execution, as long as you're not detected during the execution. The cool thing about that is the attack chain is actually broken if you were to use something like a dropper to drop that DLL into the folder and then continue on with some kind of benign action, because the next time they restart their computer will be when the malware starts. So it breaks the attack chain as far as being able to tell when the file was dropped versus when it was executed. So in conclusion, I threw some training up here. Like this thing is like way too big of a subject for an hour. That's why I kind of flew through it at the pace that I did. But I did want to say there are some awesome blogs and some training that you should check out. The 0x Pat blog, he writes a lot about, or wrote a really awesome series on how to get around sandbox detections, that kind of thing. But there's also a gentleman, the Cocomelon C. This guy, every time he learns about a new malware execution technique or some kind of privilege escalation, some kind of bypass, to understand it, he will write code in C++ and figure out how it works, and then he puts the code out there for free. So a lot of these can literally just be downloaded and executed in your environment just to see if it works. But the code's right there too if you want to audit it and make sure there's nothing fishy going on. As far as training goes, Sector 7 puts out a bunch of awesome malware development courses, and they're dirt cheap. They're like $230 a piece. There's like 7 of them, and they're worth their weight in gold. Like there's a ton of information there. Even cheaper is the Malware Dev Academy. Those guys, I think for $500 you get lifetime access, and they're constantly adding new things. And you get access to just an insane amount of stuff. I'd be remiss if I didn't mention we've got the Intrusion Ops course. I think we call it Red Team Tactics now, where we do red teaming from beginning to end. But we do have a pretty heavy section on developing malware. The White Knight Labs guys, they do an offensive development course. I've taken it myself. It was really awesome. 0 Point Security, Rostamaus, he has the Red Team Ops courses. There's 2 of them, one on how to do red teaming and one on how to just generate malware that will get around EDR. Some resources here, just basically some GitHub repos that I wanted to highlight. I know I'm running out of time here. So I will say the one thing that we do use paid-wise is this ballast kit stuff. That gets us around a lot of EDRs because those guys actually put a lot of effort into generations that do get around this stuff. But the rest of that stuff is free and definitely worth checking out. So real quick takeaways, malware development's field all on its own. This talk was an inch deep and a mile wide. Again, there's no way I could get through all that in an hour. These are really all just kind of jumping off points for self-study and research. But if you can understand the methods here, you can also understand why your protection methodologies are being bypassed. And a lot of times you can kind of shore up any holes if you put in a little bit of time and figure out how to get that up and running. So I'll open it up for questions. We got a Discord if that's your thing. We've got the Wednesday Offensive every Wednesday. We have people come in and we talk shop. We talk about offensive things. So if you're interested in that, check us out. If you want to download the slides, that's a link right there, redsiege.com/payload. It's a PDF. I swear to God, there's no malware in it. That'd be like a crappy thing to do, be a security company and then, you know, try to hack you. But no, seriously, all the slides are right there. So any questions? All right. Hey, thanks for coming.